Good evening, everyone, and welcome to tonight's webinar featuring the Casio Prism. My name is John Deal, and I've had the privilege to be a mathematics teacher for 33 years, the last 20 or so years with this wonderful learning and teaching tool, the graphing calculator, and it's a privilege to share some thoughts with you this evening using the learning tool. Tonight's topic focuses on the subject of probability, and probability can be a difficult topic for students and even for teachers. We're going to look at some explorations this evening, and most of the explorations we're going to look at are intended that you could duplicate the experience or modify it, of course, as you wish, for use in your classroom with your students. A little bit of what we do is really intended to be teacher background, to provide a little bit of additional information as to the underlying mathematics of what we have there. The major topics that we're going to look at tonight are also available to you in a handout form. Here's the first page of what that would look like. If you've registered for this evening's webinar, we've sent you a copy of this by email. If you are listening to this as an after-the-fact recording, please do notice in the same place where you found this is an opportunity to download the PDF that accompanies the webinar. So hopefully you are able to have that either for your reference right now or even to look at later to kind of recreate some of what we've done. I think the most important message that I hope I can share with you this evening is to contemplate the idea of probability as a relative frequency. In other words, if we were to do something, say roll the dice, and we did it many times, what kind of results do we expect? The particular outcomes that could occur, with what frequencies do they occur? And in the long term, what frequencies occur? And even more interesting, what relative frequencies occur, expressed as a fraction or a decimal? That long-term behavior is really the essence of probability and how to help students understand what's happening. I encourage you in classroom activities to actually do some collection hands-on. In other words, if it's about flipping coins, do so. Spinning spinners, rolling dice, drawing items out of a hat as a classic. All of those are useful activities and help get the sense of two things. What is the problem that's being explored? And secondly, that there are in fact random and varied outcomes that are going to occur. However, it's also very useful to agree that for looking at an extended number of trials and to look at many outcomes that occur, another great opportunity is to use simulation, to simulate the random activity, in this case this evening, by the calculator itself. So we're going to take a look at some simulations and some results that we get and relate them to the underlying theory. And so let's get started. Here we have our Casio Prism. I of course have split the screen just to make the screen a little easier to see. And we are going to start with icon number 1, the Run Matrix menu. So to get to that particular place, the easiest way to do that is to push 1 on the keyboard. Again, if you're just a little bit new to the Casio Prism, we have these different icons. You can use this cursor and move it to highlight the particular icon, but it is easier to note that each icon has a character. The first 9, of course, are these digits. After that, it's a single letter. And that's a little bit simpler way to choose a particular item. So again, I am going to choose item 1 by pressing this 1 on the keyboard, and that would bring up the Run Matrix menu. Now what we want to do here first is use a random number generator, or actually the way we're going to do this particular activity, we're going to use random integers, and there is of course a difference. So we want to find how we can generate those. So what we want to do first is in the second row of our keyboard, find this key, OPTN, abbreviation for option. Option brings up some of the things you can do on your Prism: lists, matrices, complex numbers, and so on. An important feature over here on the far right is this arrow that of course is directly above the F6 key when your calculator is not separated like this. And that really means look at the next page or look at additional choices. So if I push F6, we now find a few other things, and the key one for us at the moment is right here at F3, prob for probability. Press F3 and we see some options including permutations and combinations, but the one of interest at the moment is the F4, rand for random. Press F4 and we see some choices. Random number. Now that random number actually would generate a decimal between 0 and 1, very useful for certain purposes, but right now I want the second choice, int for integer. So we're going to generate a random integer. Press F2. We see it actually shows rand int number. It starts with a parenthesis. What you need to put inside the parentheses are the first value and the last value from which you want to choose numbers that is inclusive, of course. So if I type 1, comma 6, this would be a typical simulation, if you will, of rolling a single die. Each outcome will be one of these integers from 1 through 6 inclusive. The way to see your result is in the lowest right hand corner, EXE for execute, and in this case I rolled a 3. Now if you're working along, keep in mind the whole idea here is that we have some random results, so that in fact your result is quite possibly different. To see a few more results, I can simply continue to press that execute key. I don't have to go back to the command itself. Each time I press execute, I will see now I have a 2 and a 6, a 5, and so on. And so we get these random results using random integer. Now for certain purposes you may want to actually see, as I suggested, one of the values of simulation is to see many results at once. We're not going to generate a huge number right now, but to get the idea of how that works, I'm going to push the up arrow on the cursor wheel, and I'm going to push the left arrow. I'm at the end of the command. I'm going to go left once more. I'm back inside these parentheses. I can put a third value which says please generate this many results all at once. So for example, if I push comma 30, this really says I would like to generate 30 random results, once again between 1 and 6 inclusive. Let's see what happens when we execute this command. We're actually given a column arrangement. This just makes this a little easier to see what happened, and I can scroll down the list. The number on the left says which roll was it. So for example, the 16th roll was a 1, and so on, all the way down to, again, we asked for 30. And so that's a convenient way to get a lot more results in a quick manner. If you want to go back to the screen where we were, you simply have to push from row 3 here, exit, and we can go back to what we had. Now what I'd like to imagine with you is that we were using this and we were playing some kind of interesting game, and you can win a prize, but it depends on the result, of course. So let's just imagine that on a single roll of a die, if you are lucky enough to roll a 6, then you're going to win a prize. So rolling a 6 is a winner. We would of course be interested in how many times did that happen out of, say, these 30 times that we played. Or we might go 100 or even a larger number to see what happens. There's actually a nice convenient way to do that. I mean, yeah, we could go back and look at those results again and just kind of scroll down here and count, and that wouldn't even be that bad for 30, but the higher that number gets, the more work is involved to doing that. So I'd like to share with you an option that you can use, but maybe a little bit of a detour of an explanation of what happens and why it works. For example, on my Prism, I'm going to type this little bit different expression. 1 equals 1. Somehow the calculator has returned a 1. Let's try one more. 2 equals 1. And now it's returned a 0. When you use these operators, things like an equal or a less than symbol or something like that, think of it as a true-false question. Does 1 equal 1? Yes, it does. When the calculator returns this 1, that means the statement as typed is a true statement. When we have 2 equals 1, not true, it's a false statement, the calculator will return a 0. Now we can actually use that logic to allow us to check results from what we have in our dice rolls. The way we're going to show this, actually, to make it the easiest, we're going to run that command again. F2, random integer 1, 6, 30. Close the parentheses. Execute. Now we have, and again, don't forget, these results are different than what we saw a moment ago because this is a random activity. I'm going to exit back. And what I want to do is look at the list, or actually have the calculator look through this list using the kind of logic we just talked about. Now one of the things that's going to help me do that is found, once again, if I go to Option, and I have the first tab under Option is List. Remember F6, let me see more. Again, and here now I have a sum. S-U-M, find a sum. I'm going to use the sum command, a left parenthesis, and I want to tell it that I'm using a list. Notice that the word list appears in yellow on the 1 key. So to access that, it's the yellow shift key, 1. Now what list do I want to use? Well, for this first example, I actually want to use the list we just created. When you have a result on your screen like this, the calculator thinks of it as your answer, the answer to the previous command that you did. You can access an answer by this key in the bottom row. That the key itself is what we think of as opposite or negation, but again in yellow, ANS, abbreviation for answer. Let's use the yellow shift key, answer, shift of the decimal point in yellow is the equal sign, 6. Now let's pause for a second and think about what is happening with the calculator in this instance. We have a list of 30 numbers that were just generated. It's looking at each number in that list and asking this question: is it equal to 6? Remember, when it is true, the calculator thinks 1. When it's false, the calculator gets 0. So there are 30 values here. Each one of those numbers, playing the true-false game, each one of those is a 1 or a 0. We now sum that up and it will tell us how many 1s were there. In other words, how many times was the statement true? That is, how many of the results were a 6. Let's try it for this example. It has returned 4. What that means is from those 30 rolls of the dice, or die, singular, actually, 30 rolls of that die, 4 of them came out to a 6. Again, if you do this again, you would expect different results. And in fact, I believe we could just do that and go back up to the random integer command and hit execute again. And that was not a great demonstration, because in that case we got the same exact thing. There we go. On the third try we see that number is certainly different. By the way, that was a little bit of a bonus demonstration that says, interestingly, on the Casio Prism, when you go up and execute a command like that, you get an update of the commands right below it. What I was saying is, when we replayed the random integer command, this result came out the same. So we saw in 3 tries we got 4 6s, we got 4 6s another time, and then we got 10 6s. So we've had 90 rolls and 18 6s altogether. Again, different results will occur because this is a random feature. Now, another way to get this type of information, actually a little bit easier way, and it's certainly more informative, would be to plot a graph of the results. I think the best name for the graph in this case is a histogram, as these are numerical results. And so that's our next exploration. Let's see if we can make this calculator plot a histogram. Now, in order to do that, the simplest thing to do is going to be to store these results in a list. There's 2 ways we can do that. One, we can go back up here once again and store the results to a particular list. Or we could actually have done that in the very beginning. I wanted to show this technique without the storing, to use this list answer command. But what I'm going to do now is store this. So the store arrow is here at the end of the 5th row. When you use that key, you actually get an arrow on the screen. Remember that list name is the shift of the 1 key. And now we could store this into any of the values we want, meaning it can be list 1, list 2, and so on. We'll just use list 1 and we'll execute that. So we've made yet another list, but now what's happened is it's also been stored into a place with a name. Let's go look at where that is. Please push the menu key in row 2. And remember, I talked about these icons. In this case, icon 2 stands for statistics, so I'm going to push 2. And this brings up what we call the list editor. And in the list editor, we do in fact have those results that we just saved. So again, on roll 1 it was a 3, roll 2 was a 5, and so on. So this turns out to be a fairly convenient way, again, to access these results. So let's focus now on making that histogram. Notice above F1 it says graph. We're going to make the graph. At F6 we're going to set this up to make sure that the graph we see is what we had in mind. So F6 to set it up. At the top it says stat graph 1. That's good in this case. Right below that, mine says hist for histogram, but that won't always be true. For example, you might discover that it says something else like pi or another value, something like this. So if you don't have histogram there, you use next page, choose F1 to change it to a histogram. Here would be where are your values you're going to use. Remember, we stored them into list 1. In this case, there's an alternate way to get the list. It's actually the better way to go here. tab F1 will say, well, which list? List 1, please. Execute. Frequency gives you an option that would be a little more advanced right now, but you could put actual frequencies next to the values. In other words, an alternate way to do this, especially if you were having the students actually roll dice, would just be to put 1, 2, 3, 4, 5, 6 in list 1 and how many times did they occur in list 2. Keep in mind, we didn't do that. We did a simulation. So we just want to use those numbers as they are. And so what we should put for frequency is actually a 1. It's the F1 key. So again, here's what it says. It says use each of those 30 numbers in list 1 and use them 1 time. And that should be a sufficient setup for this histogram. When your setup is ready, go to the row 3 and push the exit key. We've set up graph 1 to actually see the results. We can push F1 that has the tab graph 1. I really like this feature. It lets you double check, well, how would you like to make the histogram, meaning where would you like to start the rectangle and how wide should it be. Starting at 0 is fine. We actually could start at 1, but I actually like having a little bit of space there. But width 1 is kind of an important choice in this example. We're going to execute and our histogram appears. Notice in this case that the value itself is actually the leftmost endpoint here. So this first rectangle actually is, how many times did we get a 1? In this case, 3. Don't forget, other situations will come out differently because after all, we're generating random results. We got 3 2s, we got I think 7 3s, 4 4s, 8 5s, and 5 6s. An easier way to do that actually is to push yellow shift, F1, in yellow it says trace, move to the right, and I can actually read now right off there. The little f, again standing for frequency. 3 1s, 3 2s, 7 3s, 4 4s, 8 5s, and 5 6s. A histogram is very, very useful for showing the results of simulation or actual probability. By actual, I mean the students were actually rolling the dice, or any other way that you collect the counts or the frequencies of the outcomes. This is a great way to display what happened and have a discussion then about what we see. I'm going to leave this graph for a minute, and I'm going to do that by pressing the exit key. I'll exit to go back. I'd like to show you an alternate that's even a little more efficient to that process. I have arrowed to the right to the second column. I'm arrowing all the way up to the top, which is the name list 2. When you're going to do the technique we're about to demonstrate here, it's really important to be on list 2 itself, not in this second row where you can put a label, and not in this row where the first value of the list occurs. All the way up the top, please. And what we're going to do is repeat the same exact generation of a random list right here. Thus, we don't have to go through the storing or anything. It's going to happen automatically. So let's try and recall, well, how did we do that in the first place, get these results? We used option. In this case, it's slightly different, I think, but probability, we certainly see that here. F5, F4 for random, F2 for integer. Now we see how this is going to work. We've got this kind of edit line right here towards the bottom of our screen where we can put 1, 6, 30. So this is a very helpful way to create the list of results right here from within the list editor. Let's press execute, and there we go. We now have a second set of outcomes for 30 rolls of the die. Let's go ahead and take a look at the plot of this. I'm going to exit out of, remember we pressed option to come in here, so we have to exit out of there to go back to graph, set this up. We have two choices. We could set this up as graph number 2, or really it's even easier just to say, oh, this time we'd like to see the histogram for list 2, please. So highlight X list, press F1, which list? This time list 2, execute. Remember, after you've set up the graph the way you want it, push exit. It's still graph 1 because that's what we chose to do. Double checking that our settings are still good. And now we see some different results. In this case, I guess if 6 was a winner, this was a pretty lucky day for us, as we have won a rather unusually large number of times for the 30 rolls. We got 11 winners in that case. So that's kind of nice to see that random results will happen, especially with a small number of trials. But let's talk about that a little further. In the long run, if we played this game many times, we would expect these results to even out. In this game, each one of the results, 1, 2, 3, 4, 5, 6, are believed to be equally likely. And so this is an example of what we would call a uniform distribution, uniform implying that the results are the same. And that is the connection that I'm hoping to make between the idea of relative frequency and probability. If I would bring up this handout for just a second to reinforce what I'm speaking of, when we look at the results that we have in long term with many different rolls, this is what we would expect to obtain. We would expect to get 1/6 of the time to get a 1, 1/6 of the time 2, and in fact 1/6 of the time for each of those values. So once again, this has the name uniform distribution, meaning we expect each outcome to occur with equal probability. With that in mind, let's explore a situation where that's not really true, with really just a minor difference. Let's suppose instead of rolling a single die, we choose to roll 2 dice and add the results together. This is a typical situation. One of the most popular games, like Monopoly, that's exactly what you do to move your token around the board. Roll 2 and add them together. Now if we think about a simulation of that, there is a caution here. We know that the results we can get would be 2 through 12, of course integer values, 2, 3, 4, 5, and so on. And so we might think we could generate values between 2 and 12, but actually that would be misleading, because, as we're going to see, those results are not equally likely. Some of them will occur more frequently than others. And so to do a proper simulation of that, it really is best to take what we've just done, where we've generated results 1 through 6 30 times, then we did it another time in list 2, and we could think of each of those as, what was the result on the first die, what was the results on the second die, and then what would we get if we added them together. So I'm going to press exit to leave the graph. I'm going to go over to list 3, just like before, all the way on the top, please. And what I'd like to ask the calculator to do is add across. Shift, number 1 to get the list, list 1 plus shift list 2. In other words, what we're asking the calculator to do is generate a third list by adding together the values in list 1 and list 2. And that is add them together respectively. The first two get added together, the ones in the second row. So we should see a 9 and a 6 and so on down the line by adding these results. Let's press execute to make that happen. So list 3 is a great simulation of what you would get by rolling 2 dice and adding them together. Let's have a look at this histogram. F6 to set it up. Simply tell it to change please to list 3. Execute, exit, graph 1. Windows settings still fine. And here we see the results that we got in this case. We got a 2 just one time, and in fact in this example we didn't get any 3s. And we got 4, 5, 6, 7. We got 8 fairly often. And so that was our results for these 30 rolls in the first simulation. It's a little hard to draw conclusions from that, given that you have from 2 to 12 giving you 11 different outcomes that could occur in only 30 rolls. It's hard to draw any real conclusions from that. I think it would be a little more meaningful to do some more rolls. So let's do that, and in fact let's use a little shortcut once again. Let's go right here in the list editor, and in list 4 let's try to play the game again. How about 100 times? Let's see what happens. But what we're going to do, instead of making 2 separate lists, we're just going to do it all at once. Remember, to get the random integer command, we're going to use Option, F5 for probability, F4 for rand, F2 for random integer, from 1 to 6 inclusive, this time 100 times, parentheses. But again, the shortcut, now I can do it again and say plus and repeat that exact same technique. The reason this works is it will generate, when it encounters the second command, it will generate different random results. So we're really doing the same thing as adding list 1 and 2 together. We're just not going to make separate lists this time. We're going to get 100 results in list 4 that occur between 2 and 12. Execute. Pretty quick. And here are the results for this random simulation. Exit. Graph. Set it up. Tell it we'd like to see list 4. Exit. Graph. Now that's starting to take shape. What we would discover is the roll of 7, which was the most common in this case, is in fact the most likely to occur. And then it decreases both to the left and the right. So the roll of 6 is a little less likely than 7, 5 a little less likely than that, and it's a tie between 2 and 12 for the least likely results to occur. We'll explore this just a little bit further. So I think my conclusion would be from what just happened is doing a simulation of 100 rolls is giving a better view of what the theoretical results would be, But still, there's clearly some difference. In other words, here I got 5 more often than I got 6, and I never got 11 at all. And so again, these are relative frequencies. Probabilities occur with long-term behavior with many, many trials. Now, I'm going to suggest a slightly different technique that's going to allow us to see what these theoretical probabilities would be. To do that, I'm going to go back to Menu in the second row, and I'm going to go to 5, Graphing. Now, in order to generate the picture I'm hoping for, I'm going to ask you to go into your setup here and scroll down a bit till you find something that says Grid. And I'd like you to turn the grid on. For example, if your grid happens to have the word off or line there, simply push F1 to change it so it says on. I'm not positive if this is necessary, but I'm going to push execute to make sure that I've actually saved that change and in fact the grid is on. Now what I'd like to do is use that grid to represent the different dice rolls that could happen. In other words, a 1 with a 1 and a 1 with a 2 and so on. For the most effective view of that, I'd like us to go here, which is V-window, or I think of it as the viewing window. It's yellow, of course, so we get that by yellow shift, F3, and we can start at 0 and go to 6, but actually for a little bit of extra space, let's go 6.5. Here it says scale. In this case, scale is rather important. The scale is going to determine how often does the grid appear. In other words, where are the dots that we're about to see on a grid? 1 is important there. Let's do the same thing for y. 0 to say 6.5, scale of 1. Save that. Now we're going to go back and generate a graph on these grids. Well, what's this graph going to be? Here's what I'd like you to think. Let's call the first die X and the second die Y. We're rolling them and we're adding together X plus Y. So let's just suppose we were wondering about this question. How often would we get X plus Y equals 4? The way to reinforce this would be to actually make the graph of X plus Y equals 4. There's a couple ways to do that, but the most common would be to change it to Y as alone. So how about Y is 4 minus X? Or if you prefer, opposite X plus 4, but either is just fine. So 4 minus X. One more time to reinforce that. That really is saying the two dice, X plus Y, would be equal to 4. Show me where that's true. If you're somewhat new to the Prism, don't forget to push the execute key so that your graph here is appearing in blue and the cursor's moved down to Y2. If that's true, then this command draw should be visible on the screen as F6. Let's push that and see what happens. So here's what I'm trying to suggest. Each one of these blue dots is an example of an outcome that can occur. This is 1 and 1. This is 2 and 1. This is 1 and 2. And so this dot right here is the only case where you can have a sum of 2. But both of these represent where you could have a sum of 3. And the one we darkened on purpose was, where do you have a sum of 4? And my point is that there are 3 places. There's a dot right there, and one right here, and one right here. so that there are 3 chances to get that 4. If you want to make that a little more obvious, you could go Shift Trace, tell it to jump please to where X is 1, press the execute key once more. That second press of the execute makes this red dot, kind of emphasize what we have. I like to think of it as a red dot of emphasis. That 1, 3 is one of the pairs of interest. Similarly, we have 2, 2, and we have 3, 1. So again, what I'm trying to use, and I'm going to exit off the trace there. Oh, I apologize. Didn't mean to leave the whole graph. So what do we really have here? We have 6 dots for Y. We have 6 dots for X. We have a grand total of 36 dots. Apparently 3 of them are dots where the sum adds up to 4. And in fact, the probability of obtaining a 4 is indeed 3 out of 36. Yes, I know that can be reduced, but the 36 is convenient to think of. And you can generate additional values. You can change the value of 4 to anything you want. In fact, here's kind of a nice option that what you could do in here is, let's go in here to type and say I'm going to convert this to an inequality. Notice how it says convert right above F5. Convert. I want a greater than or equal to. That's F4. That's pretty good, although I observe, there we go. And we draw that, and now we see that all of these shaded dots would represent where did we get a sum of 4 or more. And again, in this picture we have 33 of the 36 dots. So it's a good way to illustrate questions like what is the probability of getting exactly 4? What is the probability of getting 4 or more? What is the probability of getting 4 or less? What is the probability of getting between 4 and 8? And you can use this grid, I think, to help reinforce, and especially the fact that these diagonal lines, as the dark blue line is suggesting, each one of those corresponds to one of the possible sums that you can get. In the end, part of the purpose of this exploration is, without getting too complicated, to talk about a scenario where there are different probabilities for the results. In other words, in exploration number 1, I was interested in a uniform distribution where all probabilities were the same. In this exploration, they are different. Again, if I jump to the handout for a moment, this whole scenario with the dots on the grid was to try to persuade you in the end this distribution looks something like this. If we use the letter S for sum, the probability of a particular sum, the probability of 2, is 1 out of 36, 3 is 2 out of 36, 7 is 6 out of 36, the most likely result, and so on. And again, one of the reasons I deliberately didn't reduce those is just to see the more obvious pattern here if they're not reduced. Plus the important idea that if you add all of these values together, you get 36 out of 36, or 1, meaning we've correctly accounted for all the possible outcomes that might occur. So that is the conclusion of exploration number 2, where we're looking at a distribution with the dice and the different results that we might get where they are not uniform. Lastly, I'd like to suggest how we could extend this just a little bit further is to agree that we've kind of thought of this as a game Originally we thought of it as here's a game, and if you roll and you get a 6, then you're going to win a prize. So we have a probability of 1 out of 6 of being a winner. You could certainly do a similar scenario with the 2 dice. If you happen to pick 7, say, okay, you're going to roll 2 dice, and if you get a 7, you win a prize. It happens to have the same probability, 6 out of 36, of course, reducing to 1/6. Of course, if you pick other values between the 2 and the 12, they would be different probabilities. That was part of the point. But let's just stick with that idea. Pick either one of those 2 games. The first game is a little easier. But let's imagine that we have this game, and the probability of winning the game is 1 out of 6. If we were going to play the game a large number of times, how many times would you win? How many times would you expect to win? What's the chances of never winning? What's the chance of winning every time? If we play the game 30 times, what's the chance of winning 5 times? Things like that, which again are looking at a little beyond just the individual roles themselves, but looking at sort of the behavior of how likely is it to get certain results. Part of what would help to understand how that works is I'm trying to describe a game where there's really a win-lose scenario. There's 2 things that are going to happen. Sometimes there's a little bit of confusion because we say, well, the dice has 6 outcomes, agreed. But if I define the game as you win on 6 and you lose on everything else, that's kind of where I'd like to turn the thought. There's a 1 out of 6 chance of a win, and there's a 5 out of 6 chance of a loss. And that type of scenario is called a binomial experiment or a binomial situation. The binomial, of course, implying the 2 different possibilities. Oh, there's a few other rules that are necessary to ensure that it's truly binomial, mainly that the probability stays the same all the time. If you have a somewhat different game where maybe that's not true, like drawing numbers out of a hat or something like that, and the probability changes, that would not actually fit what we have. So how might we do this? I'm going to go back to menu, back to run matrix. Although it's not necessary, I'm going to do an F2 delete just to clean up the screen here. Delete all. Yes, I do. There we go. Now, of course, if we wanted to ask a question like, play the game 30 times, how often would you have no wins, 1 win, 2 wins, and so on? We could, of course, simulate the game a lot and keep track. Conveniently, there's a shortcut that would not require you to generate all the rolls and then go down and count. Even though I hope you found that useful as our initial exploration, either by using the sum command or by creating the histogram, there is in fact an even faster way that'll help us answer that question, how many times did we win? So let's try something just a little bit different. Return to Option. Press the F6 to go to the next page. F3, probability. F4 for random. But now, this is why I was trying to use the vocabulary word binomial. This bin, which is of course the abbreviation for binomial, turns out to be exactly what we want. Press F4. Now, here's where you have to know which order to put these things in. And what we're going to do is say, suppose I played the game 30 times, and the game we're playing, I have a probability of 1/6 of winning. Again, the most basic example would be, as we've already stated, roll a die. If you get a 6, you win. That simple command, 30, 1/6, is going to return how many wins did we get out of the 30. Press execute, we won 5 times. If you press execute, we won 5 times. Oh, but this time we won 7 times. There really is random behavior going on. We won 5 again. 3. Interesting, I think we had 5, 5, 5, 7, 3. That's 25 times. So on the average, we won 5 times. The reason I find that interesting is that turns out to be what you would expect. Why would you expect that? Well, you're playing 30 times. Each time there's a 1 out of 6. 1 out of 6 of the 30 would be 5 times. Will you always win 5 times out of 30? No, there's some random behavior going on. Sometimes we have less than 5 wins. Sometimes we have exactly 5 wins. And sometimes we have more than 5 wins. We see the numbers tend to be centered here near the 5, and it would be very surprising to get a really, really large number of wins when there's only a 1 out of 6 chance of happening. To explore that a little further, let's continue to generate some of these, but let's store them for convenience. So, menu, number 2 for statistics. Let's go to the next available list. In this case, it's list 5, and put that command in again. Option, probability, random, binomial, 30, comma, 1/6. But wait, I'm going to put something else. I'm going to put 100 here. Now what does this mean? This means we're going to play 30 rolls 100 different times. In other words, please record how many wins out of 30. And then again, how many wins out of 30. And then again, how many wins out of 30. And so on. Do that 100 times. Let's press execute. Now there's a lot going on with this to play 30 times and keep track of the results and do that 100 times. So we saw a wheel up in the corner for a moment, but now the results have been stored here in list 5. It is unlikely but possible that we got 0 wins. It is actually extremely unlikely but possible that we got 30 wins. So each result is some value between 0 and 30. And again, trying to make an important distinction here. These numbers are not outcomes on the dice now. We kind of bypass that for a little faster result. These are how many wins did we get. How about one more histogram? Exit back to graph. Set it up. This time list 5. Exit. Graph. And here we see the results that we had. I'm going to do shift trace. Apparently twice. We only won the game once. 6 times. We won twice. And so on. Remember where we were saying on the average we would win 5 times, and that is in fact the most common result, although 6 wins was very close to it. 7, 8, 9, and we never won more than 9 times. So this again is a simulation. I would call these the frequencies. We could divide them by 100 to get what we might call relative frequencies. In other words, 22 times out of 100, 0.22, would be the relative frequency for 5 wins. Now, going to try and conclude with how might you figure out an exact probability for this number of wins. And I think the best way to explore how that would work would be to contemplate a simpler scenario for a minute. And so what I'm going to do is go back to this handout for a minute. And let's suppose for a minute that we only played, instead of 30 times, suppose we played 3 times. If we play 3 times, then the probability of winning all 3 would be 1/6 for the first time, 1/6 for the second time, 1/6 for the third time, and multiply those together. And that would be 1 out of 216. So again, even just playing the game 3 times, it wouldn't be very likely to win them all. Now what if we say the probability of 2 wins, and by that I do mean exactly 2 wins. We've already taken care of 3 wins. There's a chance of winning 1 out of 6, of losing 5 out of 6, and so this multiplication right here, 1/6 meaning we won, and then we win again, and then we lose. But that's not quite the entire story, because that meant we lost on the 3rd try. Perhaps we lose on the 2nd try. So again, I've tried to use the letters to reinforce that. WLW or LWW. And so in the big picture, the chance of exactly 2 wins would be 15 out of 216. Because these 161656 are the exact same expression except for the order in which they occur, we could shortcut the whole thing by looking at it this way. We're going to have a 1/6, we're going to have another 1/6, we're going to have a 5/6, and that happened 3 times. And so here's a little easier way to get the result. In a very similar way, if we said what's the chance of exactly 1 win, it would look just like that, except it would be 1/6 one time and 5/6 twice, and we see that that is a bigger fraction, 75 out of 216. And 0 wins would be 5/6 times 5/6 times 5/6, or 125 over 216. Thus we have our 3rd distribution, which would look like this. If we played 3 times, how many wins would we get? And notice the good news is 125 plus 75, 200, 215, 216. 216 over 216, the total is 1. So now if we go back to the more complicated question, which is, well, what if we have 30 rolls? We can see that we just have to use a 1/6 for each win and a 5/6 for each loss. But if we ask ourselves this question, how likely is it to win the game exactly 5 times? Well, it's this combination of where do those wins occur that becomes a little bit complicated to compute. So we pose this question: what is the number of ways that 5 wins and 25 losses could occur? And fortunately, we have a very nice built-in shortcut that tells us that number right away, and it's called a combination. How many different combinations could we make of W's and L's if we had 5 W's and 25 L's all together? Let's take a look at how the calculator does that. So menu 1 to go back to run matrix, and I am going to once again go option, show me more, next page, F3 for probability. Now we've been using RAND, but now I want to borrow that combination symbol, and here it is right here. And so I would put a 30 and the combination symbol and a 5, and that would tell me that important how many different ways are there to order the W's and the L's. All of this is sort of background that would say something like this. If you wanted to know what is the probability of exactly 5 wins, you could type 30, then use this combination symbol, 5, multiply that by the fraction 1/6, that's the chance of winning, raised to the 5th, because the question again was, what's the chance of exactly 5 wins? And if there's exactly 5 wins, then there are exactly 25 losses, 5/6 raised to the 25. Let's look at these numbers one more time. Inside the parentheses, 1/6, that's the chance of winning. Inside the other parentheses, 5/6, that's the chance of losing. The exponent 5 comes from the question. What's the chance of winning 5 times? Losing 25 times. The 30 is the entire number of times we played, and the 5 again corresponds to the number of wins. If we execute this, we see that we have roughly a 19% chance, or 19 times out of 100 we would expect to win 5 times. I don't remember what we had on our graph. I'm just going to jump back there quickly because I'm curious about what we had for 5. And we had 22 there. So that was just a little bit higher than theory would predict. In conclusion, though, I do have some good news, which I hope makes this a little friendlier exploration. The good news is all this is built in, and we don't have to remember all this complicated formula. Let me illustrate that. I press Option, next page. I apologize, I didn't need to go to the next page. Option, F5, Statistics. And I've tried to use this word a few times, distribution, for the distributions, how many times do results occur. F3 for distribution. And there's our friend, our vocabulary word, binomial. Binomial distribution. We're just going to use the first one. That actually stands for binomial probability distribution. If you're really curious, the second one stands for cumulative. If you ask questions like 5 or more wins, let's just illustrate the first one. And now we have to know a little bit about what order should we put these things in here. And I believe the correct order is, if we were going to play 30 times, and we use the fraction 1/6 as the probability of a win, what is the probability of exactly 5 wins? And I hope we see that same number. We did not. My apologies. I think I'm typing these in the wrong order. There's actually a better way to do this, which I wish I had done, because that's not an effective demonstration to put the numbers in there in the wrong order. Forgive me. Could it be this way? Nope. I'm going to show you the alternate way, and then maybe we can figure that out. The alternate way is to go into Statistics and find the distribution command there. And the advantage in this location is it just prompts you right away. So I know that I should go 5, 30, and 1/6. Execute. Yay, got the result I was expecting of the 0.192. So that's actually the better place to go. It does lead me to believe that maybe that was the correct order, 5, 30, 1/6. And I certainly should have known that, but I just wasn't coming to me honestly right off the top of my head. And I always use the other way. That's better. Well, our time is certainly up here, and I thank you very much for being part of the webinar this evening, or even thank you to those who might listen to this in the future. I hope we've given a nice exploration of a few different ways to explore with probability, especially the idea of simulation and the idea of creating histograms, but also a look at some of the theoretical results. And I hope that persuades you to kind of adopt the idea that probability is not best learned by a bunch of memorized formulas. Probability is probably best learned by thinking about what does it really mean, which is the relative frequencies of long-term behavior. Once again, thanks very much for joining the webinar, and I hope you enjoy teaching and your Casio Prism. Good night, everyone.